Okay, good evening and welcome to Hurley London offices. We are really happy to have you here today for the CIBSE Society of Lighting Daylight Group seminar. So I will just say hello to the people who knows me and well, they don't know me. I'm Maria Gonzalez Matterson. I work in the lighting design team in the Daylight Group. So we are very passionate about daylight. So I just say a couple of things about we are not expecting any fire drill today. So if you hear the fire alarm, please take the way out through the stairs, please. And also the toilets are out in the lift lobby to the left. So I think apart from that, I will present the presenters for today, John Margalevich and Stephen Cannon-Brooks. I hope you enjoy the talk and give you the.
So I'm just here to hand over to John. But when he gets up, he'll come and join me here. So I'm going to introduce John, then he can introduce you. John is Emeritus Professor of Daylighting Simulation at Loughborough University, and also visiting professor at Eindhoven University. I don't know whether I've missed any roles he's already acquired since I last spoken to him, and he is currently the chairman of the Daylight Group, which, when he introduced me, he will remind me he's a successor. He wasn't very pleased with the idea, but he hasn't quite chalked up as long as I have. So we're almost on an even keel, aren't we? So the Daylight Group has been in existence for I think probably 4 decades. I don't have an exact date on its founding, but it's been a forum within CIBSE with a certain degree of independence from the Society of Light and Lighting, as an area where people can gather to discuss the use of daylight in buildings, simulation, prediction, analysis, measurement, and above all, most importantly, is understanding what it looks like at the end, and which is perhaps the most challenging bit. Right? Though we sort of take it for granted. Right? And over the years, we've had a series of group meetings and visits, things of which this is the latest. And it is an opportunity for people to present research and experience amongst a very enthusiastic audience. I can always assure you of that. And today, we're going to be looking at how we think about the use of daylight in heritage buildings. And can I hand over to John, who's really going to do most of the presentation?
Well, I'll just introduce Stephen. Well, Stephen's sort of introduced himself. So me and Stephen have worked together for nearly 20 years. At least the first time was on the Hermitage in St. Petersburg on the daylight modelling for that. So Stephen is well known for his lighting design work, but also his daylighting work, and particularly demonstrating that scale models were not everything.
I take great pride in launching John's career.
There you go.
Because I managed to demonstrate that the tools that we used in the past were not accurate enough to give adequate simulation for daylighting complex interiors, anything more than a white box, that is. And as a consequence, and John has taken on the mantle of proving how well we can do it using software.
Now, I'd just like to introduce Nigel Blades. Nigel commissioned these projects over a period of 12 years, I think. Oh, okay, quite a while.
Yeah. We're a team on this.
Yes. So Nigel, would you just like to give just a little bit of context?
Can I introduce Nigel briefly? Because Nigel has even longer set of connections, because Nigel used to be a lecturer in UCL in sustainable heritage. So at a point we could call ourselves colleagues. I think hopefully we can still do that. Absolutely. If we may. Okay. And he moved from there to the National Trust and to take over preventive conservation and we're now, along with John, collecting more titles. As you're now, are you confirmed or not?
I'm interim head of collections conservation.
Right. So Nigel is one of the most senior members of the National Trust as staff. So it's a great pleasure that we have him here. Also, as part of our team, because as he was instrumental in initiating the work that John and I are going to introduce. And I'm very much hoping that Nigel will be able to answer questions about how it's been used and applied over the years, because it's been going on for such a long time, and it's been a learning process rather than one just discrete study and finished, if I may.
Okay, thank you very much, Steve. Thank you, John. Just to say a few words. So I work in the conservation department, if you like, at the National Trust, and we've had a long interest in daylight, and daylight is the principal source of light in National Trust houses for display of collections and historic rooms. And it's always been a tricky thing for us to manage, because we have to work on both the provision of enough daylight for people to see things adequately and well enough, and also to manage that light, which can be damaging and corrosive for collections items, for fading of colours and also damaging to materials. So that we've always had to balance those two elements. And we saw the opportunity initially 12 years ago, talking with Stephen and John, to progress some of our work with simulation, and we're going to hear about several case studies from trust properties where we've used that simulation to help us understand the fall of light inside our interiors and to make adjustments to the interior which can manage and control the light in the way we want to do that, and also to predict fall of light in all sorts of different scenarios under different regimes of how we operate blinds and how we use daylight in different orientation of buildings. So it's been a really fruitful collaboration. It's an ongoing partnership, so we've got some other research ideas we're still wanting to explore, but it's a delight that John and Stephen are able to present this for you, and I hope you'll find that interesting, and very happy to answer questions for you at the end as well. So I'll hand back to John. Over to you, John. Thank you.
Right, thank you very much, Nigel, and hopefully I've set everything up now so it will not go into screensaver mode like it just did then. So
you've stolen a painting from somebody.
Actually, my daughter did that when she was about 10. So, a little bit of background. Hardwick Hall, which I'm sure you've all heard of, more glass than all, probably the most highly glazed building in the world when it went up. So that's the great gallery space. Tapestries there, sort of big side-lit expanse. Spaces, most heritage spaces are characterised by often side-lit, not always, but often side-lit. And so you have huge gradients of illumination throughout the building. And you'll have measurement taken only at 1 or 2 points. And measurement devices can be passive, like the blue wall, which slowly fades in a controlled manner. And so that's for cumulative exposure over many months or even longer. Or you can have logging at 5, 10 minute, 15 minute intervals with a wirelessly connected lux meter like the Hanwell there. So as mentioned, so a little bit of simulation history there. This was probably one of the earliest images created with gradients back in 91 possibly, or 92, and just started tinkering with this package. No one knew what to expect from radiance back then. There was no documentation to speak of. So it was a matter of experimentation. One of the things they did was to create this sort of daylit space. There's roof lights above. Those are actual baffles to block direct light coming through the glazing. And of course, one of the things that we're interested in is not so much the visual appearance, but the illumination of light falling onto those objects. So this was under an overcast sky condition, and you can see there those sort of ceiling baffles. Again, I'm not a designer, that's just playing around, but it's done a reasonably good job of providing fairly even illumination across those surfaces. That visual impression image these are actually the first true high dynamic range images, and each pixel is a measure of the physical brightness, candela per meter squared. Now, for the simulation, it actually has to compute the light falling onto those surfaces before it can make the luminance image, but it's a very computationally inexpensive part. The difficult part is computing the light that's falling onto all of those surfaces, and then the luminance image is simply that illumination, fall of illumination modified by the reflective properties of all the different materials that are there. So, moving on now a number of years, simulating a long-term exposure of an artwork to daylight. So using CBDM, climate-based daylight modelling. So just a quick recap for people who haven't heard this. So prediction of any luminous quantity using realistic sun and sky conditions, often hourly, for a whole year using standardised weather files, or actually or monitored. And increasingly, I think there's a lot interest in actual meteorological years based on monitoring data. So the first project that Stephen and myself did with Nigel was Mount Stewart in Belfast. Actually, Stephen got to visit, I never did. Also got to go on the roof. So the concern was this painting, which I believe is possibly one of the most valuable in the Trust stewardship.
Yeah, one of the most iconic and famous paintings.
So Hambletonian rubbing down. So Stubbs, this was painted, I think, quite late in his career.
About 1800.
1800, right. It's on the great staircase. It's underneath a large roof light. And the conservators were concerned about the illumination that was being received there. So you've got very bright cupola just below the roof lights, you can see there. Here's a 3D model that was created based on a laser scan. That was the IWEC data for Belfast, not too far away. Not the sunniest place in the world, as you can see from the direct normal illuminance there. And it was a relatively straightforward matter to predict the cumulative annual illumination in kilolux hours. That's actually showing the whole area, but the part we're interested in is the painting, and here it will just slowly fade into the illumination map across there. So you actually see quite a gradient from about just over 4 to just under 3 megalux hours per year across the painting. But the advised maximum was 600,000 lux hours, so 600 kilolux hours. So according, going by the simulation, this painting was receiving 4 or so times more illumination than we'd like. Interventions in any heritage space always need to be done carefully and with quite a lot of consideration for a whole raft of reasons. So here the intention was to examine these interventions with simulation first. So one of them was to reduce the reflectance of the environment, in particular the cupola. One of the nice things with the simulation is you can unpick the different components of illumination and find how much light is arriving directly from the glazing and how much is being reflected around. It turned out that the cupola was highly efficient in terms of its high reflectivity and shape for transporting light down to the painting. So we looked at the, called it cupola, the dome there, reducing that reflectance, same for the walls. Woodwork's not important really because it's such a small area in the space. Another issue was the transmission of the roof lights. Now this was an old, was it wired glass? I think, again, we weren't sure what the transmission properties were, but luckily Stephen was managed to get on the roof and there was a bit of it that was actually hanging over. So I managed to clean that up and put a light meter above and below and actually get a pretty good estimate for the light transmission or the actual glazing. So that was very lucky that that design just lent for that. There had been a manually operated system, I think, a shading system above there.
Mechanical blinds, yes.
Yeah, mechanical blinds. And with all the weathering and stuff, they failed. Like, it was just a matter of time with those mechanical systems. So one of the things we considered was actually kind of a marine mesh. I think it was it's mainly used for sailing.
Mesh, that's right.
Yeah. And so I sort of measured the transmission reduction effect of applying this mesh over the glazing. So we tried those separately and in combination to see their effect, and together they gave, certainly in terms of the simulation, results which were much closer to what the conservators were hoping for. Now, we didn't end up with as much validation data as we'd hoped. In fact, it wasn't really enough to be definitive. It looked like it was heading in that direction, I think, what I recall. So here are the photographs of the finished space. I believe there was historical precedent for the choice of colours there.
Yes, that sea green wall colour was used throughout the house in the 1920s, so it was recreated as a colour now.
And as for that, I don't think people even notice that there's anything over the roof lights. Provided the weather data is reliable, the simulation results are probably pretty spot on. One of the nice things about doing a space like this is there's no human intervention and there's no operation of blinds, because the moment you have human agency changing substantive properties of the transmission elements in a building, then simulation becomes hugely uncertain. I mean, the most reliable simulations with shading systems are where those shading systems are automatic. And provided there isn't much in the way of manual overrides, then hopefully that would work. So overall, I think that we felt that was a successful application of CBDM, and importantly testing out those interventions, which are very costly to do, and you certainly don't want to sort of feel that you've made a mistake from that. The next part was much more ambitious, because I don't know if we actually let on to Nigel at the time, but we didn't know exactly how we'd do this, but just thought there was a very good chance. So this was now to use measurement to deliver what you previously could only do through simulation. So the technique we chose was high dynamic range imaging, now where you produce a high dynamic range image by camera. So this is just using ordinary consumer digital cameras. Take a sequence of controlled images. The number you take depends on the inherent dynamic range of the scene. Ideally, you want to do this with the camera tethered to the computer rather than manually adjust exposure a dozen times and whatever. Okay, so here's an outdoor HDR image. This is a tone mapped HDR image, so the exposure has been varied. I mean, it just looks a bit like a sort of not too great ordinary picture, but the important factor here is the luminance value behind every pixel. So that's a logarithmic scale. So we're going from 40 or less up to 70,000 candela per meter squared, the very bright bit of circumsolar region. You'll notice I carefully made sure that the sunlight wasn't streaming straight into the camera. You can record the luminance of the sun, but your shutter speeds aren't fast enough, so you have to resort to using very powerful neutral density filters if you want to do something like that. So HDR gives you something like that, but that's what we want. So we're almost sort of attempting to do through measurement what in simulation happens in reverse, where simulation first predicts the light falling onto surfaces and then gives you the HDR image. But we're going to start off with the HDR image. Now, it's actually quite a straightforward relationship between the two. And well, one of the terms that's been used where you're deriving illuminance from HDR is illuminance proxy HDR imaging. And the setting for this was Ickworth House. I believe it was chosen because the staff were particularly enthusiastic about being involved. It wasn't chosen by us because we would have chosen a much simpler setting, but that turned out actually it worked out much better by having all these confounding factors, as you'll see. So here's the room that was chosen, the smoking room, and that's actually a HDR image from where the camera was installed. So it's seeing two walls, the opposite wall with the door and a large wall there with the chimney breast. So we wanted to predict the fall of daylight onto those two walls. You can guess it's going to be something like this. This is just made up. We're not looking for trying to recreate the little shadowing around the chimney breast, all these things. It's the prevailing illumination field, not the tiny little details around objects. So there's localized microclimates, not interested in those. So the simple relationship is the illuminance is equal to pi times the luminance that's seen divided by the reflectivity of that surface. But this is assuming that it's an ideal diffuse reflectance. But you look around, a lot of these surfaces are. A little bit of colour there in the beams, but ceiling, the grey part there, a lot around this space is diffuse. Now, let's just say you were looking at the ceiling and two walls. Say there's two walls that have got different reflectances. They're on the right, and the ceiling's got its own reflectance, row 1. If you take a HDR image of those two walls and that ceiling, and you just multiply that image by pi, where every pixel in there, and then divide it by this reflectance or albedo map, then you would derive the illumination that produced that brightness that was recorded in the HDR. And if you've got an empty room like this with nice even walls that are very simple to identify, you could just create an albedo map like that very easily. You would just generate it and say, okay, you know, paint this, you know, this is 65% reflectance, this is 55, and the ceiling is 75. And you could generate the illumination.
Of pure research, we would have started with that sort of room rather than
exactly
the heritage interior of the complexity that you just see.
This was research that's done by sort of guerrilla methods, not the normal grant-funded approach. Practicalities. We wanted long-term autonomous capture. Autonomous because it was miles away. We wanted to match the frequency of logging by the illuminance meters, which was 10 or 15, I think it was 15 minutes at a time, that one, I think. So we'll go for 10 minutes. Every 10 minutes there'll be a HDR capture. And ideally, if we could leave it there for months, unattended, get rid of all the dark images. Again, we wouldn't go by the clock because people could switch the lights on in the middle of the night. They do weird sort of candlelit tours, I think, sometimes, yes. I didn't know that was happening once when I was looking through the data. I thought, what is going on here? These weird patterns. Automatic backups, a fail-safe drive. There was no Wi-Fi network. Well, there was one probably at the top in the manager's sort of domain, but there was no way that was going to get through all those walls, and you couldn't set up a repeater and all of this. So there wasn't a phone signal in the room. So there's no way that this kit could phone home and say everything's working okay. So we had to be fairly certain that it would work. So one thing we thought of was we'd set this up with a consumer digital camera, this headless Mac Mini means there's no keyboard, no screen, nothing. And it would broadcast a status web page, just saying you could check that the capture's still going on, which did work, but people in, everyone working in the book had lots of things to do anyway on top of that. So this checking up got overlooked, which is, that's just the realities of working in real world settings. So the kit there was being installed for one of the monitoring periods. So this was 2014 was the first one, but that was really just trying things out. We didn't get much usable data from that one, and we changed things around an awful lot because there was a lot of experimentation going on. But it really kicked off in 2015. So the laptop there is just to set everything up. Cameras up on the wall in the corner, and then this Mac Mini and a backup drive would be tucked under the radiator. There's the camera with a little bespoke bracket that was made to hold onto it, and those are the two screws going into the wall. Why do I make a point on this on the slide? Because if you ask for something like that in a National Trust property, that's the first response. But it got elevated and approved, I think, eventually and stuff. So we could proceed. So there's the smoker room, HDR image. When you take HDR image, false color map there just to show that range of brightness there. Because once you've got these images, especially when you take images with no daylight whatsoever, just artificial light, then you can subtract the electric light, but when you have both daylight and electric light, because the electric light is relatively constant and stable. So you need an awful lot afterwards to unpick these various components of illumination. Another thing you have to do, and this is a matter of course in any HDR imaging when using a wide angle lens, is you need to account for vignetting, because you probably noticed this just in ordinary photography, the brightness drops off towards the edges, and so you need to measure that in the labs and then apply a correction factor so you get flat response across there. So right at the edges you can see it's down to about half of the response that it should be. So that's applied in circles across the whole image. We managed to get, I think, 6 months plus of unattended monitoring. And the first thing we did, because there was a lot of data, was for every non-dark image, in a day, was generate a daily sheet that showed you just this overview of what was happening in the space. So you can see there's just electric lighting, and it's nearly all blue. Here's some bright sun coming through the French windows there. Gives you a nice idea of everything that's going on in the space. There are actually 3 sets of lights. There's the far wall with the door, there's the long wall, and actually the wall that we can't see, we can actually see, although we don't image that wall, we actually see that light just peering out over in the field of view. So what we could do then was just annotate these images automatically, just to test for a number of pixels around clusters where the lights are, and then you just got this visual record of where the lights are on and so forth. That was important later on when we needed to separate out the electric light and remove it from the combined daylight and electric lights. So that equation, very simple when it's a diffusing surface of constant reflectance, but what we intended to do was use the wallpaper as a standard reflector. It's not terribly standard form there when you see it, but if you take a large enough sample of the wallpaper, you can treat it as fixed, and I'll demonstrate that. we concentrated on what we thought was a large enough sample there. Measured the illumination that was falling onto it and generated a reflectance map from the HDR image for that wallpaper. So now that reflectance varies between about sort of 0.1 and 0.2.5. There's a sort of histogram plot. So this paper is hand printed. So you don't get these two sharp peaks, which you would have for the light and the dark areas. You get quite a spread because of the way it's been printed and the fact, you've got this blurring of, from one to the other. So the average reflectance for the image was 15.7%. The next thing to do was to determine what was the minimum size that we could deploy over randomly without having to think about it. It was the minimum size that you could deploy that would give you a reliable reflectance value. There it's a little bit too small, and you can see you're getting quite a difference from 0.13 to 0.156, whatever. So just progressively increased the box dimensions until it arrived at a stable result. And that meant we could just pick, as long as we kept to that sort of size. So that's twice the minimum safe size. So we can still go smaller than that and it should be okay. So back to the HDR imaging. Oh, I should mention that we have one data point there for Hadwell logger. Importantly, that's up on the door, so it's really just getting the prevailing illumination field. If it was on one of the items of furniture, it would be recording very much a localized illumination field, which is not going to be the same. Okay, so we apply the vignetting. So to every image that was taken, apply the vignetting, subtract any electric lights that might be on. And this patching scheme was fixed. So it requires a bit of judgment, this part. You need to pick out patches that had a relatively free view into the space, that weren't too close to a shading object, because then you're getting a very localized illumination field. We want something which we could use that would be, if you were taking a fisheye image from the center of that patch looking normal to the surface, you would see pretty much the entire, the room. You wouldn't see big objects right next to them. So we're not going to try and resolve the illumination around the chimney breast. So if we treat all of these patches as standard reflectors, we can determine the illumination at each of the patches. And if we've got sufficient patches, then we can interpolate across those target patches and get the prevailing field. And for that particular HDR capture, that's the interpolated illumination field. That's the light that you can't see. So we thought we've got something that's promising. But now, yes, ghostly encounters. The National Trust has a whole section on houses that are haunted, and Ickworth wasn't on the list, although perhaps it should be after this, because when you take a HDR image, a sequence, you've got people in the room, you have lots of ghosts. Those ghosts don't bother anybody until they get in the way of some of the patches. Like that. Sometimes you can see there's very fleeting images, people moving quickly. And that's what happens when a ghost interferes with a patch. As that reflectivity was assumed to be 15.7%. The top of that gentleman's head was probably significantly higher, and so it resulted in a bump in the illumination map for that. So we need to get rid of these ghosts somehow. Anyone hazard a guess? I should say anyone that hasn't seen this presentation before.
You have to hum the tune.
Turned out to, well, this we didn't anticipate, but it actually turned out to be quite straightforward. And that's each patch has got a unique pixel signature. And so if you have a reference image of an unobstructed patch, and then when you compare that with an image of the same of that part of the that patch where somebody might be in the way, and you plot the pixels, what you should get is just a line that varies in slope if you've got no interference. But if you have ghostly interference there, it completely messes up the correlation between the reference and that moment in time. So that proved to be really effective. So you see the patches in black are fine. I think the correlation coefficient was above 0.8, better than 0.8. And these are where it was below 0.8, but also some I think should underline, double underline, particularly low ones. But you can see you've even got ones where if you eyeballed it, you wouldn't think there was anything wrong with that patch, but that fleeting ghost nevertheless interfered with the luminance pattern sufficiently to show up with this test. It needed to be a very efficient test as well, because there's a few hundred patches and there's thousands and thousands of images, so you don't want anything that's going to take too long to compute. So just on that particular one there, that's that's a different one actually from the one I showed you before. That's showing its effect there. As long as you're not removing too many, it should be a relatively reliable workaround. So that's the cumulative illumination in lux hours for July 2016. Again, how reliable is it? Well, I should just mention, so this is really the first time that we've been able to reproduce through measurement something that previously you could only do with simulation. So there was a validation point here. So this is showing the daily totals for, can't remember how many days, but it looks like it was about 100 or so days or more. Showing the HDR against the daily dose there, and actually pretty good. Generally, there was a few days of HDR capture fail. Again, that was one of the many things that were discovered. Why was this HDR capture failing sometimes? And we discovered it's because the volunteer in the room, because at least you can start off and it's pretty cold in the day, so they plugged in this space heater on the same extension lead that the Mac Mini and the camera were on, and it created, we think, a little spike along the USB cable up to the camera, and there was no way of fixing that with through a timed job or whatever. The only way you could restart that connection was to actually shut down the computer and start it up again. So this problem, which never would have been encountered in a controlled environment, we solved simply by having one of those timers, plug timers. So at midnight, it just switched off for 5 minutes, and then the most you would lose would be that day's data if you had connection failure. There was external monitoring was going on as well. So this is to give a baseline measure of what was happening outside. There was also the possibility of using this to validate CBDM, so we did CBDM simulations of Ickworth as well. There was actually quite a lot that was done that was never published. Something I think we just didn't have the time to get around that. However, I should say this data has proved invaluable years later, because this was first went up in 2015, I think. And I've just written a paper, well, the whole thing on it was claiming that satellite predicted illuminance was actually really reliable, and we should consider that as perhaps an option to standardise weather files. And the validation data came from that. So that was never intended, but again, there was like a lot of the work we done, all these spin-offs which weren't anticipated. So that was, I think, one of the real attractions of working in this way was the sort of the risk component. Well, I don't say risk, I mean, yeah, came out, but it was not having to really, well, justify too much, because I think what happens in an awful lot of research, when you spend an awful lot of time justifying what you're going to do, you actually just end up with incremental changes, because everything that you do is kind of everything that's gone before. And that's, yeah, sheep. So we had humans interfering with the equipment in the room, and when Nigel went to download the data from this device, so it was tethered with wires, was it 4 wires?
Guy ropes. Yeah.
Guy ropes, because the meter needs to be kept horizontal. And one day Nigel went, wasn't horizontal, but he found the culprit because there was telltale bits of wool. I think the sheep was using it as a back scratcher or something.
Human sheep.
So it then, I think, got penned off.
Got its own little fence after that.
Yes. Okay, so Stephen, Nigel, if there are any sort of questions at this point, so what we'll do, we'll take a few minutes of questions from the floor, and also we'll alternate with questions from the chat.
Can I
So first,
make an observation?
Oh, please.
One of the challenges of, and I may be about
Go a
to
bit nearer the
paraphrase
speak, maybe.
anything that Nigel's going to say, is that for a long time, since the introduction of conservation-derived targets for the amount of exposure in historic interiors in a museum, is we've struggled to be able to understand them well, in part because the cost of actually measuring these types of interiors and the amount of daylight present was really hard, substantial, not just because the equipment was difficult and expensive in itself, particularly the data loggers, but also in terms of how much effort was involved in doing it. Nigel will happily fill us in on quite how many dosimeters the National Trust deploy across its range of properties. But to get a sense of the distribution of light, as John has put in his simulation slides, which is in a part, we could see what the target was before we started, was finding a way of doing it was the challenge here, to provide Nigel and his colleagues, and beyond that, with a much more fine-grained understanding of the performance of daylight in interiors, because we knew that close to windows, for instance, you're going to have far more intensity than away from window. We all know that, but we just don't know how much. And then I think which we need to remind ourselves is that unlike the first interior we saw, which was a rooflit interior with nothing moving in it, so it's basically a passive lit daylit interior. Most interiors actually have to introduce some active system control. And to be able to form that control system, we need, and on behalf, I'm talking really on behalf of the trust here a bit, a much closer understanding of what actually was happening. The ultimate goal being to try and to systemize and simplify that control of daylight to make it less onerous and less risky. And the primary means of control in side-lit interiors are shutters and blinds and curtains, which all involve staff doing something. They could possibly be automated, but in a grade 1 listed interior, putting more wiring in is a big challenge. Now, it is being considered in some areas, but I'm not sure you've got to that stage.
It's probably a niche solution. It's not going to be a widespread solution.
So that what we're looking at, and the generator of this is both curiosity, but also in terms of management and about how to use daylight in an effective, but also a safe way. Sorry,
So one of our big learnings from that particular study was around the fall of light. So actually knowing the concentration of light and intensity of light at different points in the room, because as you say, we understood that would fall off by an inverse square law roughly as we go into the room. But actually to see that quantified in an example, both from simulation and from HDR, was really useful for us. And there are projects where people have carried out monitoring of a large tapestry where they've had a grid of maybe 20 or more individual sensing points arranged across the front of that tapestry. So a really inelegant and labour-intensive way of collecting that data. Whereas with the HDR approach, you can have a camera set up facing the object, so you're not putting anything in front of the object, and you can collect a similar sort of answer to your question about what is the fall of light across that tapestry using the HDR imaging technique with that little bit of preparation and study that John's now pioneered with giving to us.
Spoiler alert for what comes.
We won't go into too much detail on that, but we've also learned things about monitoring as well, and the things that can influence a monitor, such as localized reflection from the surfaces nearby to the monitor, for instance. So all of that fed into our practice. A lot of the simulation, I don't think we'll talk a bit more about simulation, or not so much.
Well, maybe at the end, I think, yes. Yeah.
So just say a little bit more about simulation.
Wait a second, can I
no, it's actually about the monitoring, is that during the course of all this capture of HDR images, we were continuously monitoring daylight levels using electronic dosimeters, so that we could make a direct comparison between what we were seeing with the camera and what we were measuring with a meter. And that's what we saw on the scatter plot. And what it does suggest, and I'm not seeing anybody's thunderbolt, is that the HDR capture system, it's quite heavy duty at the moment, and provides a reliable way, an accurate way of representing illumination across a wide field. And this is, I unashamedly say, it's the first time it's really been done.
long term like that, yeah.
Yes.
I mean, this was consumer kit. It's off the shelf.
Well, we wore out a few cameras. And
yeah, the shutter is £100. Yeah, the shutter eventually just failed because I think I worked it out as 150,000 shutter movements. Now, do we have any questions at this stage? Yeah.
Actually, I do have a question about shutter. So I know it wears out, but before it wears out, the actual time you open it up actually changes. So
you might, yeah, there was a little bit of drift to that, but we didn't notice. I did look to see if there's anything systematic, and I don't think it was that great. I think it must all happen towards the last sort of bit, and I think one of them as well. I think the room actually got closed off, but the camera left running, so it was actually data that was all dark anyway, so it didn't matter. But yeah, and if we were to do it again, for sure. Now things have moved on with Raspberry Pi cameras, because back then the camera technology wasn't great. Now you've got some very good chips, but more importantly, some halfway decent lenses. So yeah, you would have something that would be entirely solid state. But again, there hasn't. I'm sure it can be done, but I haven't seen comparable validation studies yet on the Raspberry Pi. Maybe I just missed them. Yeah. So yeah, you'd avoid all the shutter and moving parts and those. There was a question, I think, in the chat.
A question for Jens Christopherson said is, do you see your study will affect future guidelines?
Yes, so the way the Trust are thinking about light is changing a bit at the moment. So the guidelines which apply in the wider field of conservation, we're looking at what's applicable for us in our particular context. And this study also informs, as Stephen said, the way we manage light, so how we might choose to close blinds and shutters, and when things are most effective to do that. So we learned quite a lot about which measures are most effective for excluding light. So from the simulation, we know that depending on what aspect your building has, simply closing the shutters on days and times of day when you're not open to visitors, you can exclude between 50 and about 75% of the light. So a very easy win, because you are excluding so much light when it's not of any use to either people visiting or people working in the rooms. So that's a really good result, because we can illustrate that and say, well, the first thing we should always do, have a blackout solution in the space as far as possible when we're not open to visitors. And we're also able to understand the effects of different blinds of the type which are widely used in the trust, and different settings for those blinds and the reduction of light they would make for us. HDR we may well be using in other ways to look at smaller scale studies of other specific light sources as well, and how they may perform. So it's something which is feeding into our practice, and we use this, we talk about some of the work done in the projects as part of our training as well, when we deliver training for our staff. So another element which is really interesting, I think, for a lot of people working in the heritage field, is the importance of surfaces in reflecting light. And it's not often assumed that it makes such a difference between the colour and darkness of the surface. People don't perhaps account for that, even though it's kind of obvious it ought to. But it was really illuminating, sorry pun, in the, I tried to avoid that pun, but it slipped out. But it was really interesting in the study of Hambletonian, how much difference the light and coloured surfaces made to the reflection of light and the light received by the painting. So that helped us reduce the lux dose, which was a very high dose at, as you saw, around 4 million lux hours, down to something which is much more manageable. It's around about 800 to a million lux hours, 800,000 to a million lux hours now. So it's not quite at what might be considered the absolute lower limit for an oil painting, but it's something close to that. And we have to be quite pragmatic in how we manage our buildings. It's not always possible, as in a museum setting, to control everything to an ideal value, because there are other considerations about where that painting is in the house, and it needs to be in that particular location, and that the overhead cupola is not easily controlled with an active solution. The blinds, which were mechanical that John referred to, actually failed because of the Northern Irish climate. It's actually a location which is only about 2 miles, in fact not even that, probably less than a mile from the sea lock. So it actually has a very corrosive local environment. So anything that goes on the outside of the building has to be very robust and simple. So the solution, which was the mesh blind, is a very simple solution and is still in place to this day and performing well.
Perhaps just to finish it off on that, given that with that side there. So that, as I alluded to, that monitoring has made me seriously consider using satellite-derived data to create an actual meteorological years. So one of the things we can do is actually maybe look back at Belfast weather over a number of years, say a decade of satellite-derived data, and see how that compares to the standardized files. Because there's, I think it's an open secret in building simulation that now you've got a variety of standardized weather files, and they've actually got quite different characteristics and different annual totals. And so the whole notion of what's standardized becomes very confounding. It was easy when you just had one file, you had nothing to compare it with. But now when you've got 4, say, for a particular location, and then which one do you choose? There's no guidance for that. So, yeah.
Can I ask?
Please.
Is there time to ask them?
I may be quite loud, so they might be able to pick it up there.
Yeah, we'll try my best. Thank you for a really inspiring presentation and piece of work.
It's only half of it so far.
Oh, it's only half of it, it's not the end yet.
Well, half of it, but still, thank you so far. I correct this. Thank you so far for the inspiring presentation. I was one thing that I was made me start thinking, like both methods, I think you can look with the existing data, both spectrally at the results that you have, like, but within a certain range, I guess, is those simulation. Would that be something that is also interesting in these cases?
There was lots that went on which I didn't mention. One thing we did was, I think, best part of a year of 5-minute spectra with an ocean optics device. I just happened to have one, so I could plug it into the Mac Mini and then could record. So I recorded spectra for a whole year, and it just turned out actually the spectra was just, it hardly changed. It was pretty boring.
Was it due to type of glazing?
Well, no, I think it's just because when you actually, because it was looking in the same direction as the camera, the spectrum, once light's got into a space and it bounces around, it's all pretty homogeneous. It's nothing like the variation you might expect when you look at the components, when you look at direct sun and blue patches of sky. Things you never actually get blue patch, or very rarely do you get a blue patch of sky actually providing any significant illumination to space, because when you've got clear blue skies, you've got a sun and it's always got reflected sunlight bouncing around. So actually it's something to certainly look at, but it's possibly not as interesting as
but over time might be, I don't know. I mean, I think in any case, it's also interesting part of the whole routine.
Oh yeah, and there is the potential to extract the spectral data from HDR as well.
And for the trust, that is quite an interesting point about the spectra, because we are interested in what is the appropriate colour temperature for display in the rooms, and how that is affected, as you say, by the reflection in the room. So different surfaces absorb obviously different spectra elements. So we are quite interested in what this could tell us about the choice of colour temperature of lighting and how that might align with daylight that we use.
Certainly, yes, that one. Yeah, the electric lighting for sure.
Yeah. Well, I guess the glazing has also some spectral sensitivity that can be considered and checked.
The blind material, I think, are usually chosen to be neutral.
Yes.
Yeah.
So, but all of those are of interest, and some of the blind materials have quite a deadening effect as well. So we want to try and avoid that as far as possible, obviously, which is neutral but doesn't completely kill the light.
Can I ask something?
Quickly.
Very quickly. It's very interesting to see monitoring for a long time, but I was wondering if in a different scenario, you could have done just a small monitoring period, let's say, where there is no people in there to avoid ghosts in the first instance, and then trying to combine that with then a climate-based modeling and to a certain degree getting all the
yeah, we've got that parked. We've gone part of the way to that. So yeah, I worked at the CBDM code to take in
having both systems and the invaluable data of real data, but for practical terms, sometimes we want to have a result much more quicker than. We
ended up producing more stuff than we could get through actually, and some of the things even that we did get through, I haven't. Didn't have the time to cover in this, but I think we need to crack on with that.
We have, for this particular building, generated a series of sample plots of distribution of dosage across the room surface, floor and walls, 4 months with different conditions of blinds, so to act as a guide aid for the house use, and also to act as a starting point as to inform National Trust house management and across their other properties. So it's a sort of an exemplar.
They use this massive simulation data, so it was all curated and then handed over in a way that didn't need programming. So exported it into a form that would work. Yeah,
set of text files.
Yeah, distilled it down into sort of Excel files, and so the trusts have used that in a kind of exploratory way.
So we've run a range of scenarios on that data to look at opening times for particular buildings and what the change of an opening regime over the course of a year has been for fall of light, how different blind settings, as I mentioned, affect the overall control of light. So it's been a very useful data set which we continue to mine, and because that building at Ickworth is fairly generic in the way that any one building could be, but it represents a kind of a sort of 17th, 18th, 19th century tall sash windowed, side lit, ground floor type of space. So there are many rooms in the trust which have very similar characteristics. So it does allow us to extrapolate in some ways for similar buildings.
Okay. Right, well, let's...
For my voice heads out. So, next. What happens if there are no patches? And one place without patches is Ham House in Richmond, or the Volury room. So this project got going on the 22nd of March 2019. So there's Nigel, Stephen, myself, and Eleanor Brembila, who was with me at Loughborough at the time, but is now in Delft University. And we set a camera up again there. I think there were some screws that needed to go.
Existing holes in the wall there. So
existing holes. It did not require.
Saved us getting listed building codes.
I was wondering why it was that particular spot was chosen for the camera there. Yeah. That's the view that the camera had of these two 17th century tapestries. Yeah. Again, these are quite valuable, I think, in their own right. So that's the aspect from the HDR camera there. And what we did here was to use a known illumination field to determine the reflectance map for the entire tapestry. Now, we guessed there was quite a lot of reflected light there as well. If you're dealing with a luminaire and you know its characteristics, the direct light you can more or less determine unambiguously based on its photometric distribution. But here there was going to be reflected light. So we thought, how do we deal with the reflected light? So I thought, well, we can't guess it reliably, but we'll do this hybrid measurement simulation where we'll create a radiance model to determine precisely what the illumination field from that lamp was, because we couldn't shutter because we thought lots of ways of getting around this. You saw you got the barn doors on the lamp. As soon as you start putting the barn doors in, you end up with penumbra effects, and that means you don't have reliable photometry anymore to deal with. So you have to measure the lamp with its barn doors wide open and then just use it that way. There isn't any way of tightening those barn doors up because the area of the panel is so large. If you had a very small intense source, then you could collimate it and shade it just onto the tapestry, and that would have been fine. But we had to work around this. So the lamp was measured in a lighting lab, just a dark room. So that was a very nice model. Yeah, so excellent fit between measurements and simulated photometry afterwards. And then looking at the simulation, this is the direct light that's falling from the LED panel in position 1 onto that wall. AB1 just means no interreflection radius parameter. And as soon as you bounce the reflectors up, it more or less converged at AB3, 3 ambient bounces. You see there, just go back. So quite a big increase, about 30–40% in the illumination across that. So we needed to account for this. So we had to do this for each tapestry in turn, just repositioning the LED lamp and then simulating for both positions 1 and 2. Another thing we did was, because you cannot disturb anything in the room. We can't move the settee out of the way without causing a kerfuffle. We couldn't shut the room off because it's a through room. And to shut it off would mean you cut off the traffic in the house. So we had to do everything from arrival, I think, about 8:30 in the morning and be finished by 12 o'clock to get the room open. So this sort of concentrated things a little bit. We were trying to get, and we managed to get everything that we needed to done in that time. But we wanted a validation data set, so we took measurements, handheld measurements across the tapestries. That was left to the tallest amongst us. Stephen had to sort of crane over some furniture and stuff and not disturb or fall onto anything.
I've had lots of practice.
So we've got a simulated illumination map, we've got a measured HDR map. A simulated and measured, the views are never going to be identical. You can never match exactly a simulated view with an actual one. So took the area and just did even only a little bit of warping, whatever, just sort of warp that illumination field a little bit just to make it kind of pixel aligned. And remarkably, when we did all this afterwards and then looked at the numbers, so that's the percentage difference between what was simulated and what Stephen measured moving across there, which is quite remarkable. I think part of the reason that's so good is that the same quite reliable Hagner photometer was used for both the measurements and the characterization of the LED panel, because you get variance of at least, good few percent between, even standardized illuminance meters. Okay, so there's that equation again. Only this time now we're going to apply it to get the reflectance map on a per pixel basis for each XY position of the pixel. So we'll just look at a little bit of the HDR capture to illustrate. There it is in its false coloured, showing the luminance in candela per metre squared. There's the simulated illuminance map, that same pixel area. So we just divide the luminance, the HDR luminance, by the simulated illuminance. We multiply it by pi, and we get that reflectance map there. So we see it's around 0.1, 2, 3, 10, 20, 30% reflectance for that section of tapestry. And I think isn't this it for the whole thing? Yeah. So yeah, did this in two panels independently and then just stitched them together for this. Okay, so the useful data capture didn't begin until a couple of weeks after installing. That's because we were waiting for the Hanwell loggers, I think, to be placed. But the useful period from April to October, so nearly 5,000 HDR images, about a quarter of a terabyte. It was the storage we had was a terabyte anyway, so we were plenty of spare. So it's an absolute sip to derive the total lux hours. You just sum each luminance image, all 5,000, well, 4,899, multiply by pi and divide by 6p, and you get your lux hours. Why is there a 6 there?
10 minutes.
Every 10 minutes, yeah, 6 in each hour. And that is the HDR derived illumination fields over that period for those April to October, and you got there 120 kilolux hours. We'll return to those Hanwell points there later on, but there's something not right about, well, there's something jarring about this image. What did the illumination field look like in the smoking room?
What can you see that you would not expect to see?
Exactly. You're seeing print through of what's behind. And whereas it should just look even, like simulation there. Nothing, you don't see anything behind it. Whereas here so what's going on? So each of the two reflectance maps was based on that single capture taken the 22nd of March in the morning. But the HDR capture period was from April until October, when the room was shutting off. And there's a number of plausible factors, but I think the most plausible Nigel came up with, and well, let's see why in a moment. So, okay, so this is now an illustration to test this hypothesis using just a simulated map and the initial HDR capture. So what happens when you don't have perfect alignment? So we'll just look at that section there. So that reflectance map was derived using that simple relationship. So we'll just move the terms in the equation round. Okay, so I just swap those terms round. And of course, I get back to the simulated luminance which I began with, which was nice and smooth, showing the fall off from this LED panel. Okay, because you've got exact pixel alignment. But what happens if we repeat that and actually misalign these two images, the HDR and the reflectance map, by just 1 pixel? So there it is again with exact alignment, and now just 1 pixel. And the print through leaps out at you. Okay, what about less than a pixel? So this managed to use I won't go to the nitty-gritty of it, but essentially managed to sort of synthesize what it would look like, starting off with perfect alignment in that top corner, and the opposite corner you got 1 pixel, and you sort of gradual change from 0 to 1 across the image. So even at a quarter to a half of a pixel misalignment, the print through will show through. This is what Nigel reminded us of. I think I dimly appreciated this in the past, but it didn't strike me, even when I was thinking about this for ages. Even in a controlled environment where you're monitoring the humidity and the temperature, tapestries will expand and contract. I think the amount for the ones in the Great Hall was they measured about 6 millimeters, I think.
That's right. So there's been a study at Historic Royal Palaces, Hampton Court, about how their tapestries change, and they will change it in real time, within minutes. They will change their dimension and weight as they give off and take moisture from the environment, depending on the prevailing relative humidity. And the RH in Ham House is quite stable, but it's not absolutely stable. So it will move between about maybe 40 and 60% over the course of a number of months.
And the typical pixel size across the tapestry from that vantage point, that camera, varied from about 2 to 2.6. So you only need a shift of half a millimeter, which is a quarter of a pixel, which is entirely likely in something like that. And I think quite convincingly, well, it's the best explanation, I think. There are other factors as well, pixel scattering and whatever, all that, but you can't fix any of those. And even if you could, this will be going on. So it's a question of, well, working with it. How do you work with it? So apply an energy preserving filter. Energy preserving meaning take the average. With a lot of image processing, actually often take the median, not the average, because you've got these very high or very low values, which are noise. Here it's not noise, it's energy that's just been redistributed. It's not a little speckle of noise or something that you want to eliminate. So just use average filtering as a multi-pass in a box, but it results in an image now like this, which you can still see some of the artifact of the filter and whatever, but essentially a much smoother representation and probably more like what's really going on. So just to compare the print through image with the filtered image, I looked at 6 segments and then the whole left and the whole right panel. And so you can see there in the numbers, the percentage difference is vanishingly small in there in the cumulative. So whilst they look very different, the actual information content across the areas which you're interested in is identical. Validation. So there were these 3 handwell meters. Now they were freestanding on little stands, and they were in front of the tapestry. And what's more, you can see, well, inevitably, because they're moved when the room's cleaned, and they're not going to go back in exactly the same place. So they've been shunted around there. And here I had to kind of do something a little bit like the Ickworth, where I had to get patches from the tapestry and then interpolate across those, missing out the interference from the movement. It means you could actually end up sort of further and further away from it. So it's not a robust way of doing this for sure. But the only really robust way would be probably to have one dangling in the middle, or a couple dangling in the middle of the tapestry, and then we'd take lots of areas around it. But then that would be good for a visitor experience to have something like that sitting up there for ages. Nevertheless, working with these, so that's the scatter plot with these are the daily dose totals in lux hours. So you've got the 3 sensors, 1, 2, and 3. 2 and 3 not pretty good. 1 is clearly out. So if we look actually at the total over the whole period, even for 2 and 3, I mean, these are the numbers that you're interested in conservation purposes. They're well within 10%. So they're pretty good. Why is that one so out? Well, I don't think there's anything fundamentally wrong with the technique, but there's something going on with the way these measurements were taken. And so this is now using the simulation model of the room. This is a hemispherical fisheye image taken from the notional position of each sensor point, looking normal into the room. And those circles are 10-degree increments. Because in a hemispherical projection, that sort of correlates to, well, equal areas in hemispherical projection have equal illuminance effect. For 2 and 3, that one is, much closer to the center of the image. Whereas for 1, it's right at the edge. Now, we know these move around, and there's no guarantee that that point was representative, because we don't have any, well, you could probably go through all the images and try and pick them out, but that would be, I did try a bit of that, but it was, the image processing is too complex and it would have to do quickly, and it would have been a flat. A slight aiming error will result in H1 will result in a significant difference in the illuminance. So I think it's because it's on the horizon there on the edge. So lessons learned from this.
We'll never get hard again.
We'll never get hard again, yes. Lots really. I think primarily it was doing stuff under pressure at times in real world spaces, but we just encountered phenomena which are real things. These are happening in these occupied spaces, used functional spaces, that never would have happened if let's say we had rather more generous funding instead of a controlled experiment and and that would have all looked very nice and it would have been very neat. But we wouldn't have picked up on a lot of these things. And these sort of techniques, which were pretty much invented as they occurred, we didn't approach any of these. Well, certainly, the first one was relatively straightforward, Mount Stewart, but the subsequent ones, a lot happened on the fly, solving problems as they were uncovered. And I think Nigel's already alluded to quite a number of sort of spin-offs from this that wasn't anticipated. It's a way of doing work which, let's say it's not the most comfortable way, but given the way it was done, the fun part was that I actually got to do all of it instead of just passing it off to a student or an RA. So that was,
Well, I think perhaps more or less cognizantly, we've tackled something which others have avoided, which was to really try to get to grips with trying to typifying what the illuminance distribution in real interiors is. Part of the inspiration of this is actually the images generated by John of simulations. So in a sense, we'd set ourselves, and I think others, a target of what we really wanted to get out of a system of analysis and measuring, which had never been done before. But we knew what the target was, as usual, I think things can prove to be even more difficult than you thought they were going to be. And it'd be easy now in hindsight to say, well, you did start with a very difficult place to do it in. And I know John and Eleonora have been looking at schools, which tend to have possibly simpler decorative treatments, though actually most schools have covered this stuff, so you probably eventually end up in the same place. I think that what we have done as a sort of set up at least a threshold, I won't call it a benchmark, but at least a point at which we now understand that as a camera-based technique can provide a much more rich typification of illuminance levels in real interiors. There hasn't been a rush to do it everywhere. I think it's a good indication and recognition of how difficult it is actually still.
I think moving over to a solid state setup which would be more reliable and would cost £150.
So one of the things which we found, which was quite challenging, was working with Nigel and his colleagues, is we tried to record what was being done in terms of management of the rooms day by day. And I think we're all happy to hold up our hands and say this was probably in some ways the most difficult bit. It was to try and get the human part of it to be able to be synced with what we were doing in terms of measurements. Actually, we often had to go back and look at the photographs to see what things. And probably if we had two cameras, we would have had one pointing at the windows to find out what state the windows were in.
Because the
because
the
these blinds
that
and shutters were opened and closed and things we were doing things. So,
I mean, real world validation of CBDM under those conditions is going to be fraught with difficulty, because you would have to have an exact schedule of the operation of all the shutters, and that in a space like that is a huge ask. I mean, the volunteers and the staff, they've got a lot to do anyway, rather than just note down every precise moment when they do something. So while simulation certainly has its uses, unless you can include the operational aspects reliably, there will be question marks over it. Whereas, of course, the camera-based methods,
that's
called what's there.
hand on heart, is one of the reasons why we've struggled to try and validate the simulations. We've done simulations of these rooms, and as you can see, they're models and things like that. But because there's so much going on in them, is to be able to separate out the data. It's proved to be a big challenge. But we've got all, in a sense, the base components, including the exterior unobstructed illuminance levels. There are a few things to do if we have the opportunity.
I should just mention, before we go on to the questions, yes, the National Trust staff at Mount Stewart, Ickworth and Ham House, who are fantastic with all of this and very supportive throughout. Lenora mentioned, who's now at Delft, and Katie Lithgow, who's there at the beginning. So, please, any questions on any of this? Please.
I am coming from energy efficiency and operational energy background, and what you've been saying was really fascinating. That now I want to ask Nigel, have you thought about using similar methodology in terms of the camera based and the way you're doing that in terms of driving energy efficiency, whether it's daylighting or fabric improvement?
We've not thought about energy efficiency in those specific ways, but we have done, the Trust does a lot of work on trying to make its operations energy efficient and low carbon. And mostly that's been around the type of fuel that we use for heating and other sources. So we've been converting our gas and oil-fired boiler installations all to renewables. So virtually all of the oil boilers, which were the majority, have been eliminated across the National Trust and replaced with biomass or heat pump systems. With lighting, we've not looked at the energy efficiency angle of lighting in showrooms so much, but in back of house spaces, virtually all of the lighting is now LED, and in showroom areas, there is a majority of LED lighting too, which is chosen largely for an appearance of the lamps that looks historical. So they look a bit like the filament incandescent lamps that would have been there in the early 20th century, for instance. So we are doing a lot of LEDs, and we've looked at a little bit of building simulation for heat loss characteristics of the buildings, but we're not generally modifying historic showrooms so much because of the nature of the fabric and the kind of limitations on what can be done. So we would put probably some insulation into loft spaces, so we would use rock wool insulation in mansion properties quite a lot. In office areas we would have secondary glazing, but in the showrooms themselves you would find they would have single glazing, and often they would be quite highly air exchanging, highly ventilated space compared with a modern building. But that actually is beneficial for the houses because they also have quite a lot of moisture exchange with the environment, and they have moisture ingress issues. There is sometimes damp in basement areas, so actually sealing those buildings up too much can lead to detrimental consequences for the environment and mold growth and other environmental issues. So we try and use as little energy as possible to get it from the most energy efficient sources, but we're not over insulating or over controlling the buildings for reducing, for instance, ventilation. So not quite the answer to exactly the question you answered, but I hope that's halfway there anyway.
Yeah, I was just asking about the methodology whether it could be applied, but yeah, I think you're giving me even more elaborated answers, so thank you very much for that.
Okay, we'll just see if there's one on the chat next.
We'll have to make one of you.
No, okay.
Hi, thank you so much for the presentation. It's really valuable to see this in practice, practical environments. Actually, I'm curious about the H1 sensor, which is different from the other. I wonder one explanation could be the imperfection, well, the differences between the real reflection property to a version. Because when you have the light coming from low angles, like the edge, the reflection, I think at angle is more different from inversion, the perfect inversion?
It's possible, but I think it wouldn't work in the way you expect. I did wonder about that, and I did try and think this through, but it was a while ago. Because the windows are quite diffusing, but you're right, it's got a bit of an oblique component, and yeah, that
comparison to
assertion
Ickworth, the sensor used for the simulate for the comparison was in a similar situation on the sidewalk.
yeah, but it's the way that we're using the tapestry patches as proxies. That's where, but I think that would be more of an issue if you were catching the kind of mirror reflection, but the camera wasn't. It was in a position where I think, because I did look for the spec, if there's apparent specular nature and zooming in on the images. So I think it's an effect that definitely does go on, but I think the other thing that I think was happening on there is you've got an illumination field which is probably varying just across the distance at which the sensor is proud of the tapestry. So whilst the specular things are definitely something there which is going on, I don't think it works in the way one would expect for this one.
And the nature of light admitted into the room is that it's all diffuse light. So you wouldn't have any direct sun because the blinds would always be down at a time of day when there would be direct sun, and that would then diffuse the light.
It's still coming in sort of a bit, it's directionally diffuse from there, but it was initially, that was my thoughts explaining the print through, but actually the pixel shift from the tapestry moving is I think a far more compelling one. Yeah. Sorry. Yeah.
Hi, John.
Yeah.
Just out of interest, do you see this having a wider application in measuring the real life daylight changes within properties as a result of other external things like development happening around the building? How would you really understand how that works?
Oh, you mean like in a right light case?
Yeah, or in planning daylight assessments, that kind of thing.
What it's giving you is illuminance, and I think it'd be good to actually just start with one point, because at the moment we don't really have illuminance data that's representative. Well, we don't really have any that I'm aware of. I don't think it's ever been invoked in a right slide case I'm aware of, or planning actual, because you need long-term measurements for a start. But then you also need to relate to what's happening outside as well. So that's another thing, the external conditions. Because I've seen in a lot of published papers on simulation where they've done some measurements and they say, and we validated it, and they say, so we did it, like in February, so we used the February data from the weather file. It's like, well, you can't do that because that's no guarantee that, weather files are unique. The only thing you can be certain of, the weather will never repeat in exactly that way, so you can't salami slice it and stuff. So yeah, getting a firm handle on external conditions, AMY, actual meteorological years, yeah. Now I'm done. Sorry, I've just you've had a couple of questions already, so I was leaving you.
Don't ask me. I've been constantly narrowing them down because I have like 3 questions, but now I'm just gonna try to ask one. No, it's also a lot aligned. I think I narrowed down to this one just to be more conclusive. Aligned with all the others trying to ask, like, it is an interesting methodology, and what do you see of the future of it? How can it be used for other purposes? Like, I think even I see potential to estimate some other indoor environmental constraints in such sensitive environments, like related to air and light and what might happen.
Well, I'm sure you can tease out more things, but
or even
in a sort of financial and practical sense, in terms of just having one installation point I don't think you have to imagine too much where you've got something that serves as both a security, duty security camera, just keep your eye on things, but there's been a little bit of calibration done on it. And a little bit of assigning of.
Well, the nice thing about
activities to
security
patches and
cameras, they're
things.
normally fixed to
Yeah.
the fabric of an interior, and nobody touches them.
Yeah.
And so ideally, if you could run on your illuminance capture and your whatever else through the same camera, that would be really neat. And it's sort of it's an idea John and I shared over decades, I think, probably.
Yeah, and I guess they're all physical properties that can be translated to each other to understand some other estimate at least. Of course, it's not, especially with those kind of camera properties, estimation, they don't have as much accuracy, but I think it's really interesting to be able to develop it to see.
Well,
I mean,
a lot of modern
it seems
security
like more
cameras
of a detective work, some of the parts you did.
Yeah, I mean,
Light detective.
The chips aren't expensive now. I mean, that Canon was quite an ancient one, the 550D. So I think it was only about 12 megapixels and maybe 15. And now I think you can get certainly. I think you just work fine. In fact, actually, especially the the Ham House one. But yeah, with 8 pixels, Tony showed you actually don't need to resolve all those things. You just end up with a cleaner print through. So yeah, 8 megas fine.
For the trust, we're looking at possibly other places where we might want to measure particularly high value items and understand their illuminance from HDR data. And while we're doing that, to be modifying window treatments and lighting regimes so we can see in real time how the light falls across an object changes. And that illuminance, we need to understand better from both the point of view of the visitor seeing things and what might be the limits of levels of luminance to be able to see well, and also for the conservation and long-term conservation implications as well. So there are a few places where we would like to do this more, and we talk about a few smaller applications as well, which can also be really helpful for us.
Yeah, but my point was that you could extract, for example, data related to photochemistry of the air around these subjects from this, and I think as the articles that you're dealing with are sensitive, this would be also. I mean, my point is that there are other information related to the indoor environment that can be extracted as well, not only the light, but the effect of light on other things.
So it could be
like air.
photochemical energy. We can derive a certain extent.
Yeah, energy was mentioned.
And we filter out, and we've also looked at the visible spectrum, but we filter out all of the ultraviolet radiation at the window, so we always have a UV film for one of the most damaging elements of the spectrum.
Yeah, but it's interestingly like even close to 400 could affect some chemistry in the air, from my understanding and readings. So yeah, I don't know. And over time, I guess it's a lot more sensitive.
Yes, there's lots of ways we can use this, and as John said, we've learned as we've gone along, and things have spun off. So I think that could well be the sort of thing we might do more.
So I think there's sort of 2 steps to this, one of which is understanding actual performance. And so the camera technique has provided us with a tool, and I think we've demonstrated that it can deliver far more information than point measurements. And it's still quite onerous at the moment, but the potential is there, and the validation and to demonstrate its accuracy. The next stage is to say, well, how accurate are simulation tools? Because ultimately, those may be a quicker or cheaper route to delivering the sort of answers we need. And of course, obviously, in new build, we want to know how accurate those are. And this is, in a sense, a backdoor route to understanding and giving us more confidence in simulation. But it's proved a lot of work to give us the information to be able to make very wide field comparisons rather than just single point.
I think the camera would pick up some of the noise as well. It would start vibrating.
The camera would bounce up and down, yeah?
Yeah, you just put one sensor there and then Focus
do
on
all the blaring for the tapestry.
I mean, the way you've
Yeah.
been detecting stuff, I guess you can get to that.
Yes.
Everything
Well,
is.
at least that only started at the end.
Yeah.
Got through the main bit.
Is that your neighbours?
I don't know where.
Time to go home.
So probably some of
Because
the
we
shots
just,
of the-
somebody's AirPod just fell out. We haven't had it on a bit.
Yes.
John, I think there's a question at the back. At the back.
Yeah, just speaking of the weather fights, I know CIBSE is doing some future weather fights because the current ones are not that useful.
The future ones?
Huh?
Sorry, the future weather ones.
Yeah, CIBSE is working in future weather fights for thermal modeling and all that. But do you think daylighting is changing as much as temperature, or there is no?
I think the jury's out on this one because I think you can't morph irradiation in the way they've been morphing temperature, because some people claim that as you put more energy into the atmosphere, it'll become more turbid, in which case then you're going to have a higher ratio of diffuse to direct sort of things. You know, the direct is going to be reprocessed more into diffuse light, or veiling type diffuse light, depending. But there's some other models that claim that the changes in the weather patterns could lead to, in some places, clearer skies. And so I think, there's enough empirical basis to do, defensible scoping studies with future weather files for kind of overheating, especially looking at, because it's elevated air temperatures over 24, over 24, 30, 48, 72-hour periods that are literally the killer in these sorts of studies. That's sensible, but for irradiation and light and stuff, a lot more work needs to be done there. And actually, I think I'm more concerned about what we're using for today's weather, actually, because when you look at different standardized files, it's like, how can they be so different? Which one do we use?
That's a merry note to leave everybody to chew on.
Well, there's lots of food left, so anyway, Chris, thank you very much for showing up, and we look forward to seeing you next week, hopefully April.